Hello and welcome to ST118 Statistics and Applications Session 10. In this video, I'd like to explore how we can apply statistics in performing this methodology or even skill set called simulation. Simulation is really more a mingling of three domains rather than just mathematics alone or a formula alone or a theory alone. And these three domains are mathematics, in particular statistics, the branch of mathematics that deal with randomness, the increasing and continuing increase in performance and affordability of computing power, thanks to Moore's law, that our mobile phones now have even more computing power than the huge and expensive mainframes used in the 60s and 70s. Right? So affordability is very important criteria because it connects to the real world, and it also is the enabling perspective, right, for this technique or methodology to be used in a more widespread areas of applications. If you have rocket science kind of technology, but it's only available to a few rocket scientists, then it won't be very popular and it won't be very widely studied, widely popularized, widely developed by other scientists who didn't have the opportunity to get that funding, that high budgets, and other students, right, and general public who might be interested in applying the theory and the technology but couldn't afford. So the increasing performance, affordability of computing power, and of course the third area is that because of that availability of high performance, high computing power at increasingly affordable costs, it becomes very easy, right, and cheap enough to implement massive statistics in real time. And if too complex cases are involved, then semi-real time, pseudo-real time, almost real time. And that has profound impact or the enabling ability for simulation to be applied to practical applications. That's why the third area, I would say, will be the business area. And my sense of business includes personal lives, right? Business basically involves allocating resources, right, and making decisions in a hopefully judicious way. And so goes with your personal life in terms of the financial aspects, economic growth aspects, right? You want to prosper, you want to accomplish more in your life as time passes by. So we conduct our life in a way almost like a business. Of course, it's more than business, right? But my sense of it is that when we come down to applying various of these topics that I've been discussing, I make no difference between whether you are running a $100 billion multinational corporation or running your personal life. You are still trying to make the best decisions. Okay, so applying simulation to practical perspectives, practical applications become increasingly easier and more realistic, more feasible, right? That means it's not going to cost you a lot. You can even experiment with it, and if you don't like the results don't make sense based on your own contextual understanding, then you may just discard the results, right? Because it's not costing a lot. Okay, so let's just document a little bit of what I have already said. Simulations, right? So simulations. And this is the main title, and it's made up of, I would say, three main areas, as I was saying. Statistics, that is math, computing, and that involves hardware and software, right? Better and better quality software, open source movements, right? All these also contributed to the widespread availability of computers and computing itself, which means we can easily apply massive statistics to business and therefore personal applications. Okay, so that's a short history of simulations development. So in a way, simulation is as old as statistics itself. Right? So it has been there in the past, and uh, we have been doing simulation, maybe manually, right? Like throwing a dice, recording the numbers. Obviously, that's not very enjoyable nor very scalable. So the kinds of problems that simulation can solve in the earlier days, while using the same theories, right, found in statistics and mathematics, would be very limited. As I was saying, computing allows not only for faster computation, but massive computation. And some of you who have been exposed to the study of AI, you would recognize that, hey, isn't that what GPU is doing as well, right? It's like trying to massively perform very simple arithmetic. Earlier on, it was simple, right? Just doing multiplication, division, and addition to help the CPU calculate faster. But now GPU is a different ball game because it's like having a lot of little tiny brains, right? So one tiny brain doesn't compare well with the CPU, a big, massive brain, but millions of tiny brains start to behave in a way that is very characteristic of itself in terms of the kinds of problems you can solve. Um, Rendering realistic graphics is just one small piece of the cake, but AI, right? Yeah, so performing calculations and statistical computing using GPU, right? So in a way, uh, trying to hold back my excitement of saying or trying to group AI under simulation. In a way, AI is also a kind of simulation of reality, of, in particular, intelligence itself. We're trying to simulate intelligence, right? When, after all, it's still a digital kind of domain, playing around with zeros and ones inside the hardware. So there's no organic intelligence in that sense, right? So we still have to train it, right? We still have to teach it and feed it with sampled data. So I'm using the statistical terms, but that's pretty much the bedrock, right? The foundation to support all these computations. Do they make sense? Do they have mathematical backing? Right? So therefore, the area of applications for simulation really, really wide. And before I continue, let me just clarify that simulation is not visualization, because visualization just tries to produce a, of course, visual image or a time-based visual image that is like a short movie or animation for us to understand the data better. And borrowing my own analogy that I used in terms of drawing scatter plots and graphs and charts of massive data, right? We are just borrowing our eyes. We are partnering our eyes as an analysis sensor and analyzer to be able to understand the data better, to draw insights. When we say understand, what is the meaning of understand, right? So it's very big. Means to extract insights. But then aren't we pushing the fuzzy word understanding to another fuzzy word called insights? What is insight? Mathematically, when data is involved, insights essentially will be the kind of pattern. You know, the kind of sense that when you look at the clouds, some people say, hey, that looks like a face. Hey, that looks like a aeroplane, you know, the clouds. But when you look at it, no, it doesn't look like it. It looks like a snowman, right? That is the kind of pattern that human brains and eyes, you know, this whole apparatus here is very good at. One look, you can recognize that pattern, right? You can shout out that figure. And that's something that even with AI, you need to train a lot, right? That means you need to have massive funding to begin with. Now, of course, you can use AI, but that just means that you are using other people's computing facilities in terms of doing that. If you want to do it yourself, you cannot. Right? If you want to build an AI from scratch to recognize the cloud patterns, like a snowman, like a cat, like a dog, you cannot, because it's just very, very expensive to to gather the data in the first place, and to uh, create that kind of data center capable of multiple trillions of calculations, so that you can get the results in your lifetime, right? You don't want to be theoretically possible, but then it takes several decades to get the results. So it's not visualization. Visualization, the purpose is to see the data, and of course, once you see it, either it's for fun, right, for science, or to draw insights for business applications and all that. So you can visualize for movies, right? So that's you can visualize for uh, image. For example, if you measure the longitude, latitude, and height, right, of a part of the Himalayan mountain ranges, you have that. Now imagine the whole cubic volume of data you have. They are correct. Right? They are real, taken from, I don't know, satellites or imaging sensors. And if I dump that whole set of data to you, uh, it will be very, very difficult to see anything. It will just be numbers. And our brains are not good at that. Right? So visualization is a technique to show it, right? And even show its changes in time. So the volume of data will be actually having a fourth axis, time. That means the Himalayan mountain, maybe you're monitoring the glacier, the snow-capped mountains, right? The snow, the ice melting, right, throughout the year, and so you have uh, sort of a periodic capture of the 3D data. And so if you have that, then it's actually four-dimensional. So visualization again is time-based animation. To show, in a way, sort of for fun, but you can sort of show to the public and say, hey, you know what, climate change is real and this and that, right? So you can do some uh, data support, because that's imaging data, right? And of course, visualization also can be used in more serious applications, like showing the uh, X-ray, right? You want to visualize the X-ray sensor captured data, right? So if you show that bunch of numbers to the doctor, the doctor cannot see any problem with your skull, your heart, your lung, your bones, and all that. But when you visualize it, right, especially if you like CAT scans, right? So they do 3D imaging of your body, and that data, if you dump that data onto the doctor screen, it's just massive numbers scrolling by, right? But the doctor can just visualize. So there's in a way, compared to simulation, there's no computational element, and all our end target in doing visualization is that picture or the animation itself. Okay, so the output is the picture, because the picture is the crystallization of uh, the the various kinds of computation, but then not in a sense of what we want to talk about when we do simulation, right? So the kinds of calculation involved will be very different. Visualization, just trying to show the image, show the animation. Um, and oftentimes we are not trying to sort of delineate the two things, the two methodologies, simulation and visualization. Oftentimes they're used together, right? So for example, we can simulate and produce results because we want that results. We want that results. The result, right, will be a set of numbers. And we can't see the numbers because simulation will produce massive amount of results. And that massive amount of results can also be time-based massive number of results. For example, if I put AI under simulation, then AI can generate 10 seconds of video, And that 10 seconds will be time-based images, right? So every second there are 24 images, and then you multiply by, say, 10, so 240 images. And if you show that 240 and each image is 10 megapixel, wow, so it's just massive numbers that makes no sense. But when we visualize it, then it is a very nice video of something that we want to see, right? And something non-existent. So we combine them both, but I want you to be able to be very clear, right, between trying to simulate and trying to visualize. We can simulate and generate the AI computed 10 seconds video and never show it, store it as a file, right? Because when you examine the file, it will be bits and bytes. It will be a computed output. That output is what we want from simulation. And then, of course, the second part is playback. So playback, video players, they are in some sense visualization software that converts the digital bits and bytes from a file to the pixels on your screen. Okay, so and next thing I want to kind of move on to is to not just stop short of trying to say that simulation has very wide area of applications and very useful and all that, but I want to also share with you what are these areas, right? And because simulation is definitely different from optimization techniques. Optimization techniques like calculus, linear programming, various mathematical branches that try to find the best location or best solution. Simulation also tries that, but the answers, the results, the solutions often have different characteristics from optimization techniques in mathematics. So it's so distinct that they are very easily separated, and they also apply to different areas of applications. So the main driver, right, applications in terms of when do we use simulation is, of course, the case when we want, right, to know, to understand. When I say know, just means to understand, to want, to understand, to be able to see, right, to know the results of systemic behavior. Systemic behavior means it's an integrated system, right, made up of components. And oftentimes, this is difficult, right? So difficult behavior. But difficult to achieve, right? When we know component behaviors very well. Okay, so this is perhaps the shortest sentence I can try to make to describe the main gist that characterize the kinds of applications that simulation is best applied to. In areas where we want, right, to know the systemic behavior. The systemic behavior means the integrated behavior, the collective behavior, the overall performance, for example. Right. So one example is, for example, in pharmaceutical drug development. So pharmaceutical drug development. Right. So it's called the computational drug discovery. I won't write it down because it's their own terms in that domain. But then essentially it's just applying simulation, right? What are the components? Well, the atoms that we know very well. I mean, at least uh, we don't know much about quantum physics and beyond quantum physics yet. But when we say we know very well the atoms and the compounds and the proteins, means at the drug discovery level, right? At the drug is like, compared to atoms and molecules, drug is like maybe a galaxy, right? So huge, so monstrous that is made up of multiple protein compounds. Proteins compared to atoms will be like a solar system, that kind of meaning, right? So it's like so huge compared to atoms. And we know these components very well, but we don't know the drug, right? The new medicine, the new compound, complex compound. And we want to know it and we want to create it. So we use simulation. Now, because we're talking about creating, so it means we need to think. And if we use humans, right, if we hire scientists, PhDs, and doctors, we have to sit down and think, brainstorm. That's what we call ourselves. But brainstorming is so slow. By using simulation, the computer will, generate millions and millions of drugs quickly, right, within seconds or minutes. And then we will be able to, we can generate by plugging the proteins, right? The protein compounds and everything, and then put them together. The question is, can we put them together? Now, some of you might already have studied this, right? I have not. But we all know that not all proteins can just anyhow be assembled. They might not like each other, right? They have certain ways of assembling, and if you don't rotate them or fold them or unfold them in the right way, they won't cooperate with each other, and so you don't have a drug. Okay. So when we talk about discovery, we need a lot of brainstorming, and that comes with simulation. Simulation basically throws a lot of dices. All right, so we will generate randomness. Remember, we are generating that randomness. We're going to generate randomness. Randomness means creativity, and that is being fully exploited in simulation. And when we apply to creative endeavors like drug discovery, right? The word is discovery because scientists are very humble. They say we're not inventing, we're just discovering what already is present in nature. Some compounds are not allowed in nature, right? So we can assemble the proteins and then discover that, hey, it's a new drug. But is this drug, that's the systemic part, right? Is this big, newly created drug? Because it's so new and we don't know its systemic behavior. What is systemic behavior? Relative to that endeavor to find that new medicine for, say, COVID-19, right? Or Alzheimer's disease, or Parkinson's disease, or whatever disease, right? So we're trying to find a new drug because all previous human history had not been able to do that. So we say, okay, go ahead, right, and brainstorm. So brainstorm is throw a lot of dices using computer, and that's what simulation is best at. So we throw a lot of randomly selected proteins, put them together. Now, of course, you know that without even knowing medical science and everything, just like me, we all know that when we randomly put proteins together, we don't know what the systemic behavior. First of all, does it connect in a stable way, right? Sometimes you can connect and then it starts to fall apart, right? Either with time or when it gets into the bloodstream of human body and whatever it is. So we're not going to talk about those. I'm just saying we don't know whether it's stable or not. Second is, even if it's stable, it can persist through time and go into the bloodstream. Would it be a sort of a poison rather than a cure, right? So the negative sides, all the behaviors, we can tell because we, relative to drug discovery again, we know the proteins very well, the amino acids, right? The reaction in the blood, we know very well. We know whether the proteins will fall apart or not upon contact certain areas. So let's put them together, right? So let's massively randomly put them together. And that is best done by simulation. So we'll have 1,000,000 new drugs. And then we filter off those that don't become stable, right? And we need to be stable for at least a year. Okay, we can simulate a year in 10 seconds. That's the kind of time compression that we can do in simulation, right? And we will want the drug to be, we don't know whether it's effective because ultimately we'll do clinical trial, and let's say we are trying to find a drug. It's not a vaccine but a cure. That means if now you suffer from COVID-19, you tested positive, you're having symptoms, just like fever drug, right? Paracetamol. You eat this new drug, you will recover very quickly. Let's say we're trying to do that. Pharmaceutical companies are trying to do that. So, what is the right thing to do, right? In the past, you'll be like, let's hire the best scientists, the best medical doctor, right, and then work as a team and whatnot. Now, let's just let it run and let it randomly find the best candidate and filter off the negatives. Right? So those that will become poison, we know what is poison, will be out. Finally, we have those that are neutral, mildly effective, very effective, maybe one super good. We don't know which one. We have 3,000 candidates left out of 1,000,000, right? So that's very good already. But 3,000, you're not going to do clinical trials on 3,000 potential trials, right? So we look at the top 10, right? So we rank them, rate them, and then look at the top 10, simulate some more, right? And for all the known body behavior, we know the components very well. We want to know what happens when this 300 drugs, 300 new candidate drugs, right? How do they react inside the body, the bloodstream? How do they do? Then from our little knowledge about COVID-19, right, and then we can say, let it react with COVID-19. Does it kill it directly? Does it suppress it? Does it surround it? What does it do? Again, we can simulate. Now, of course, this sounds more and more exciting now, right? It's like we finally can animate, right, everything. And simulation, by doing so, tells us new thing. Don't you see that this is very different? Because in the traditional optimization techniques, we basically know the terrain very well. We know the X, Y, Z axis. We know everything. Just find me the spot. What is X, what is Y, so that Z is the highest point or lowest point or the best point. But in pharmaceutical development, drug discovery, and all these simulation outcomes, typically, right, and the exciting applications are typically the results are not known to human. So like this drug discovery means no one in humankind had known this drug before. And once you have identified it, of course, then you proceed to clinical trial and all that, right? So that we already have shortened the drug development from last time, maybe 10 years, to now 6 months or even lesser. And that's thanks to, in a large part, simulation techniques, right? That we can find and discover the COVID-19 vaccine and roll out internationally, right? Because once you have clinical trials, it's successful, you're going to convince, right, the various authorities, regulators, FDA and whatnot, and then other governments that this is effective and this doesn't have side effects and all that stuff, right? So it will take many years in the past, but thanks to simulation, we have shortened a lot of the simulatable part, right? Like discovering a efficient drug, right? Clinical trial, you still have to go through that rather manual but necessary period of data collection. That means the outputs of simulation touches reality, right? So what happens? We still have to go through that. But the long periods of brainstorming, validating, does it work? Is it efficient? And so on and so forth, has been so much shorter, right? So that's one huge aspect and contribution. Simulation always tend to contribute new, unknown results. If it is your company performance, because your company performance, all the data, everything is internal, so we can easily say it's not known to the rest of the universe, right? But even for the internal people like CEO, management, and everyone, the outcome of a simulation is still not very clear. That means they can't tell from their own personal judgment, experience, everything. They can guess, right? So usually they speak confidently. Yes, this will work. Yes, no, it won't work. But simulation will kind of validate that, build from the ground up. So because we know the basic sales department behavior, advertisement that we send out, the so-called conversion rate, right? We know these from past data very well. What will happen if we go into a new city, new town, new country, right? New region, and we do the same? What happens, right? So in a way, we want to simulate our business, and that is the outcome of which is a systemic behavior. We know our component businesses, the functional arms and all that stuff very well, right? But what will happen when we move to a new region, new market segment, new product, new customer profile, right? When you want to go into a new area, what is that systemic output? That is, what will our business become? Will it be successful or not? If it's not, then thankfully, right, we didn't even try. When the simulation indicates success, right, that means positive, good. We don't know whether it's good or not, so we still have to roll out carefully with risk management. But at least now we are armed with all the knowledge of the past and the superior randomness that computing facilities produce by, you can imagine shooting a million arrows at your defense wall, at your proposal wall, as a sort of a wall of defense, and see whether it breaks or not, right? So we can do that. And another area will be, of course, in simulation of flight simulators. In simulators, thanks to simulators, we know the wind, air, cloud in some sense very well, right? The weather of a particular region or city. So if you want to train to fly, to take off and land in Singapore, Changi Airport, right? Equatorial region, very hot. Sometimes huge storm, right? And thunderous storms, and sometimes windy, right? So how do you land? So can we simulate a windy day? Can you land safely? Can we simulate a thunderous, stormy weather? Can you land safely? Right. So all these we can, like, we know the weather very well. We know the whether it's Boeing or Airbus, right? The design is very well. We can implement those because they are man-made, right? And weather elements, we study the climate in Singapore, and then we know it very well. We can implement those component. So my component can be weather. Component means those that interact, put everything together. How do they interact, right? So that's the systemic behavior. So I hope by quoting the examples, you can broaden the sense that the component doesn't have to be Lego blocks, although they are, right? They are elements or functional units, right, or environment that interact with each other. So all the components interact, resulting in a sort of a collective behavior, systemic behavior that we want to know but don't know, and very expensive to know, very difficult to know, such as, can I land safely? Can this trainee pilot land safely or not under a thunderous, stormy day that you cannot see because the rain is so thick that you can hardly see 100 meters away, right? So how to even land safely? So how do you depend on the instruments? And we know the design of the instruments very well. So we implement that, and we have a realistic big screen, not in the 70s and 80s, right? But now you can have a big screen, very real. You look at the monitor display, it's almost like looking out from the actual cockpit windows. So with that, we can train, and then of course if it crashes, right, and there's a lightning, that affected some instruments, right? So we can all make lightning happen, can make electronic failure happen, right? We know these very well. But systemic behavior, the trainee pilot's gut reaction, right? The amount of training he or she has had, will that come to play out properly, right? To land that simulated aircraft safely. So once we can talk about flight simulator, we can talk about other simulators such as driving, right? And in Singapore now, I hear they require you to also go through that simulated driving to make sure you are aware. I think that's a good thing because then you, as a beginning learner who had no experience at all on the roads, how do they drive? How do fellow Singaporeans drive on the road, right? As you might know, people in California may drive differently from people from New York. So they might be, I think this is a joke, but what I heard here was like New Yorkers was drivers. They tend to be very impatient. And one joke was about when the traffic light turns from red to green, between the traffic light turning to green and the honk sounding behind is 3 milliseconds. That means they are so impatient that if you don't start moving or you don't anticipate that the light will turn green and start moving, you get honked at. So anyway, so that's just trying to say that the environment, the component, that means the environment in which the trainee driver is trying to get used to or train in can be different. And we can switch that, right? Say, okay, you agree to New York. All right, let's try it out, right? See whether you can get used to it. Okay, so that has positive utility value, not just being fun, being nice on the eyes, that's all. No, we learn something, right? So we get something out of it. I can quote another one, which is like CAD/CAM software, computer aided design, computer aided manufacturing, right? Kind of software which assist in designing various things, such as various electronics circuits. Right, they're getting much more complex these days, and you don't want to have a human engineer now. In fact, we cannot cope, or a team of engineers. That was the past, and you have slight risk that despite seasoned electronics engineers examining the design, there may be a slight chance, slight in terms of relative chance. 1% can be very little for human engineers to look through. And for that 1% of the chance, the finalized circuit layout board, when it goes to manufacturing, can be having problems, short circuited, not connecting properly, whatnot. So there normally will be a prototype. So let's produce 100 first. So at least, when we test it out, it doesn't work, then we can redesign again without having a lot of write-off costs. But even just producing 100 is going to cost something, yes. But cost is at least a sort of a risk mitigation, so it's justifiable. But what is not very justifiable is the time delay, right? So after the first prototype, you go and correct the circuit, you prototype again, because what makes you think that the second prototype will be perfect, right? So you prototype again. So all these sequences of prototypes will extend your lead time to market, right? So for example, you are trying to produce another iPhone-alike mobile phone, right? So it is like quadruply foldable. I think Samsung is introducing that now. You can fold and whatnot. Okay, so you have to design that, right? And then try to manufacture it. So you produce that prototype and then change, and then produce again and then change. It will delay your launch date. So when other companies, maybe Apple, maybe somebody else, launch it in 2025, you end up having to push back to 2026, therefore losing the entire market. Because people, when they first bought the phone, it won't immediately change, right? I mean, some will, but most people won't change immediately, especially when it's like super duper very expensive models. So then you lose out one whole bunch of supporters in that sense. So CAD/CAM software, but my favorite is still building software. So those software that allows you to helps the civil engineering architects to build buildings. So in areas where you have earthquake, we can't say Singapore has no earthquake. Let's not be very complacent. Singapore may have tides, right? So high tides due to climate change. But that's going to be decades later. But decades can be soon. So if our software can simulate when tidal waves come in, let's say Singapore gets flooded for extensive periods, 1 month, will the soil soften and then the whole building starts to shake, tilted, collapse, right? So all these we can simulate in advance because we want to know the systemic behavior. We know the bricks, the foundation, the weight, the physics of buildings very well. We know the flood effects on soil, erosion, whatnot, and that part of the ground, right? Sometimes the bedrocks they are solid. Sometimes it's all soft soil. So we know it through our experiments and sample data. But when floods come in and stay there for long periods of time, will the building sustain itself, right? And for areas such as in Japan, where they are very susceptible to earthquakes, it is mandatory, right, that they have buildings that can withstand at least earthquakes to certain amount levels that are common. So how do you produce that earthquake digitally? Correct. So simulation has this effect of like making a digital twin of such a shaking and see if our components, the building that we intend to build, maybe it's in Yokohama, maybe it's in Shibuya, right? Roppongi or whatnot, right? A new building, will it stand this minor earthquake? All right, so Japanese buildings are well known to be able to tolerate such shaking through their design, their materials, their engineering, their works. But of course, you don't want to build a building first, then test and see if it will stand. You can now use the software, right, to digitally shake it first. That digital shaking is not for fun or just randomly shake. You got to shake it in accordance with physics, in accordance with geological behavior of that part that you're building, right? For example, that part of the area is coastal area. That will behave differently from areas in near mountainous areas, right? So you got to simulate based on the input data from that area and then digitally shake it in accordance with physics and geographical theories and knowledge, right? And the shaking, there are many ways of shaking because vertical shaking might not be the same magnitude and frequency as horizontal shaking. And vertical shaking and horizontal shaking will have different shearing forces on the building, resulting in different probabilities of collapse. So you cannot just write a program, shake it, hey, yeah, it's shaking on the screen, finish. We're talking about very serious mimicking of reality, and then our output will be reliable. So the quality of the output, right? The quality of output will help us make decisions, millions of dollars of decisions, and thousands of lives of decisions, because it's not just those people living in. When the building collapses, neighboring area people, cars, vehicles, assets, properties will all be affected. And so this decision based on whether the result coming out from the simulation software, simulation software says it's stable. So okay, after considering everything else, yes. But our confidence derives a lot from the fact that we have shaken it 1,000 times, if still not happy, 1,000,000 times, and it still is standing there. Okay, out of the 1,000,000 times, 0 time occurred, that the simulated building collapsed. So our confidence comes from that. But if it doesn't collapse, is it because of your program that says if collapse, then set collapse equals to no? You know what I'm trying to say, right? That means you hack it, you cheat it, and you don't allow that building to collapse. That's cheating, yes, but that would also look quite realistic, right? Because if we don't examine the code, then we won't know that that has happened. So our confidence in making decisions based on simulated outputs will have to be also transmitted to the serious implementation of physics, knowledge about reality, knowledge about the components, and we implement them very seriously. No shortcuts, right? No direct replacement with constants and all that. We have to compute, we have to calculate based on known rules about the components. Then and only then we have confidence in output. So we don't want to see a sort of a game output of a building to be built in real life in Tokyo, highly populous area, and then say go ahead and build when our confidence in making that decision is really based on a game output. That's like so ridiculous, right? So simulation software, yes, it looks very much like games because we are trying to shake the building, right? And from the game perspective, that is not very fun. But from the application perspective, we got to make very serious one-to-one, right? No compromise kind of computation. When physics says that, we implement that. When physics in real life, we cannot do that, then we stop it from happening. In reality, if it causes explosion, then we will make it explode with certain probability that is based on real life probability. When we don't know the probability, like for example, if the fire ignites in the building and the building is basically a warehouse and stores fuel, what's the chance that it will explode? Okay, so in real life, we know that it's going to be 92%, right? So unless you are so lucky, you just cannot avoid getting the whole warehouse burned up. So we implement that probability. You cannot have shortcuts and say, no, our warehouse is very fire tolerant, so 0.50. You cut it, right? So we have to do this very serious implementation. Then we can have very good confidence in the output, right? So all simulation products will produce outputs, and perhaps it will produce outputs that we like the drug works, the building doesn't collapse, the trainee pilot can fly and land safely. But when we decide whether to give the certificate to the trainee pilot or not, we have to rely on the confidence that the simulator is correct, right? And that confidence lies in the quality of implementation, or the seriousness in translating reality, physics, programming into the correct code. That is the part. That is very important. Okay. And we might add car crash. Right? So automobile manufacturers, they are required to test if their cars can withstand, crash into the wall that doesn't move, right? Like crashing into a mountain wall at certain speeds, right? And then still the seatbelt is there, the airbags release, the driver, passenger, they are safe. At least the neck doesn't break. So how do you do that, right? So yes, in the past they build a car, final car, and put in, of course, the mannequin and then attach sensors. They still do that, but then when you do a car crash, you know that it is irreversible. So irreversible kind of situations, how do we test that in a more affordable ways, right? So of course, the car companies will have to write off certain test costs. But if we can do it cheaper, then why not? So here comes simulation. So of course, all automobiles will have their designs in the digital software, right, before manufacturing. So you can use that, all the numbers, put it into simulator, and let it run. Let it run, and the running of the car got to follow physics and kinetics and everything that we know about cars. And that model, for example, that car is built with certain first gear turning ratio, second gear, third gear, and when does it switch? Because it's auto gears, right? There is a pre-programmed, based on RPM, based on timing, based on fuel consumption, whatever it is. So we have our simulator for this car crash. Will have to import those parameters for this car. In other words, this car is a component that we know. The mountain is also a component, but it requires less parameter to describe. It's just a fixed wall, right? So basically, it doesn't crash, it doesn't disintegrate, it doesn't run away, unlike a passenger, right? A pedestrian. So it's going to be there, and we will crash it. When we do crash it, right, the car may disassemble, may fall apart. Sometimes they're designed with the intention for the engine to fall apart. Of course, the car bumper is going to crash, right? And that is supposed to take away the momentum, take away the shock. Then the engine will, fall apart to further dissipate the heat, the energy, the momentum, so that the remaining forces that hit onto the passengers and the drivers will be then very comfortably absorbed by the airbags and seatbelts. Right? So that's the whole idea. But does it work? Right? So we crash them, and we have to move those components as components. So the simulator will have to like move it, not like a single car, because if you have a single car, then to the simulator there's no sense that the components can fly apart and take away the momentum and the heat and the energy. Right? Then you're not simulating physics seriously. You're just having a game, just having a car that is visualized. Right? That's not the same. So to get a simulated car crash, we input all the components of the car, whichever can be taken out and all that. We input, as you can imagine, it's going to be like 10,000 components inside and digitally integrated together to look like, I don't know, Toyota, Vios, Corolla, whatnot, right? So, and we then digitally accelerate from 0 to 100. And you have to follow the gear change ratio, engine burn rate, and whatnot, right? Just follow seriously and accelerate it to 100 kilometers per hour. Then now, crash. When it crashes, we have to follow the physics of the momentum, the energy, the heat, and everything, and the car itself, how crumpled it is. Right? If the metal is thin, then maybe, right? Maybe that the whole rear wheel will also run into the wall, meaning that even if airbag and seatbelts are working, the passenger drivers and everybody else will be crushed, right? So you have to be able to produce that kind of result if you are a serious simulation for car crash testing. And when we do get to that level of the simulator software, it will save the company a lot. Because in the past, we might have several iterations, right? Each iteration of the model design will need to run maybe a few, 5, 6, right? That's a lot, right? Not just in terms of the cost of the final car, but all the time taken to do the crash and analysis and all that. All these will be very much eliminated. The most critical part is the time, right? So it saves the company time. Let's crash it. Let's crash it a million times. None of those times the digital car resulted in any problem, right? Airbags, everything, all the passengers are safe, no injury, no neck breaking, anything. Okay, let's do a real mannequin test. Then you almost for sure, right? If your simulator is very serious, almost for sure, the real car crash test will also be the same because the simulator is so serious that it is mimicking the real car crash test, right? So that's the value added uh, from simulation itself. Okay. I just want to quickly give another two broad categories, right? All games basically are simulations. Okay, you can have shooting games to shoot the aliens, so the aliens are simulated. We don't need to have real data about aliens. You can say, hey, we don't have any sample data from alien, right? You can fascinate, imagine, create random aliens with random or designed capabilities. So that part is a lot easier, right? But if you need to mimic reality, it's a lot harder. So games, when the aliens come shooting at you, you shoot back. You want the aliens to also move randomly, but somewhat coordinated. So in the way they are both directed yet random. It's like a bunch of aliens come shooting at you, right? So they maneuver all towards you, but at different angles, at different speeds, firing different weapons that you cannot predict, right? Or as unpredictable as possible. But then games are game design companies are masters of statistics and statistical distributions. They have to tune those distributions so well that the random number generators that ultimately guide the aliens shooting at you will be both hard and easy, right? So it's hard and, in a sense, very hard to predict, so that it is mysterious, it is challenging to gamers. And it is easy because if it is so hard that no one can break through to level 2, then very soon the game will flop. Nobody likes to play. It's so hard that it's programmed for to fail everyone, right? So words get out and the game will flop. So it has to be easy enough, right? And hard enough. So that's why to tune it towards human behavior and maybe teenage behavior, child behavior, right? Depends on who you're selling to. It is requires a very very good sense of the probability distribution, and that is exactly what game companies are doing. It doesn't have to be alien shooting. It can be plant versus zombie. If the zombies come at you too quickly, if they before you can get ready or before you recharge your sunshine and flowers, they are already at your door, and you always kind of perish before you can even shoot at anything. Then what's so fun about it, right? Nobody will play it anymore. So again, for any kinds of games, it can be Pac-Man chasing you. Right? If the Pac-Man, moves too fast, then you always fail to get out of the maze in time, right? If the Pac-Man moves so slowly, you always can get out. It's like no fun. I'm going to do something else rather than play this dumb game. So again, you got the game designers have to tune the distribution, the random number generator distributions very carefully in order to profit. Right? Ultimately, it's about their business, and their business is about whether they can capture that statistical distribution in human through their games. So let's leave it as that. And of course, movies, right? Toy Stories from Pixar, right? And now also Disney and Frozen, right? Various almost real life look alike, but we know it's computer generated movies, right? Mortal Kombat movies. They are also realistic and they are mimicking real life. I mean, of course, there's this genre of there are many subgenres of digital movies. This genre of digital movies that where the characters are trying to look like real life humans, such as the Mortal Kombat movie, and there are also others like which are cartoons, but then they are also having a lot of the movements, right? The movements of the arms, legs, and whatnot, they have to mimic humans, right? So those are also computer generated, or we would say simulated animation. Right? They simulate this character, this that character. They simulate the flowers. Look at this Lion King. Right? It's again the more contemporary versions of Lion King look very real. The grass, the hairs of the lion's mane, right, and then all their eyes, right. They have veins in their eyes, even the teeth, right, looking so sharp, and yet with a taint of the wilderness of the animals. They are looking so real, and they animate the behavior, right, because the way uh, wolves and foxes jump, they are very different from those of the lions and the tigers. So all these animations make it so real that we want to see it. Kids are so excited at it, and they can make the the impossible happen. Like the Lion King is being huddled by the gorilla, right? The gorilla looks like a real gorilla. The lion baby looks like a really furry lion baby, and that those don't happen in real life, but in the movie it is possible. So to do that, we have to simulate the components, right? Like baby lions, the adult gorilla, and then they summon the animals from the jungle, right, to come to meet in this grand meeting and celebration. And all the animals must be simulated. The way horses run will be different from the way leopards leap and the cheetahs dash, right? So all these need to be simulated from our real life knowledge about the animals. Those are the components. But will the systemic output, that is the movie itself, be captivating? Now, of course, that in part depends on the storyline. But suppose the storyline is, it's well tested in the cartoon days, so it will be popular. It will be attractive. But will the output, in other words, the visualization of it, will the output look real? Now, visualization shows that scene, just showing it. And just showing it requires a lot of things like ray tracing and everything, all that stuff you know about GPU trying to help improve performance. That's that stuff. Very low level stuff, right? Simulation deals with the for example the kinetics of the legs of the animal. So when for example when the legs move, the head has some sort of a cyclical moving back and forth for the cat animals like leopards, cheetahs, lions, right? So that part, if it comes out, it looks so real, but it takes so much of scientist knowledge uh, to know and make it happen because you have to implement the spine in order for this to come out naturally, right? Of course, in such movie making, being super scientifically correct is not the main idea. So sometimes they also basically enlarge the model. That means they just describe the fact that the head will move, but not trying to mimic the physics behind the skeleton and everything. But those are just sort of optimizations, trying to reduce the complexity because ultimate goal, the ultimate systemic behavior is the entire flow of the images. That means the movie itself. Does it look realistic? Because realism is what they are trying to simulate. Okay, so all these are not just for fun, right? For pleasure, but they are about life and death, right? They are about profitability. They are about whether successful business venture can happen or not. And so it is very crucial that simulation be done uh, in a way that respects the physics that are involved, right? And there are also the choice of the particular statistical distributions that are applicable when we perform the computing in the business area that we are trying to apply it. All right, so let's just summarize the kind of criteria or characteristics, right, for simulation to be used, to consider using simulation techniques. So, of course, usually it is complex because we can describe the complexity through the individual components. For example, we want to know, does the universe expand or contract? Right? It's a complex question with a complex answer. We cannot answer directly. But what we can do and study will be the components, right? The galaxies, the movements, the stars, and so on and so forth. So we can then put them together and simulate to get an answer. Typically, it is also futuristic, right? It doesn't mean all the characteristics have to be in place, but if it is future oriented, we're talking about whether the universe expands or contracts, right? So this is like if you fast forward far into the future. Okay, so it can also be time compressed. So time compression or expansion, because these are not easily doable or even possible. Uh, Impossible situations. Right? So I will just use these descriptions that when you see those cases, maybe you can consider simulation, right, as one. So time expansion is about we want to know the future, way, way into the future. For example, will how much of Singapore will be subsided, right, in seawater when the tidal waves come in 30 years' time, 50 years' time, due to climate change. So we can, of course, assume that every year there will be certain degrees of or fractional degrees of increase, and if we do nothing to stop the climate change, and then the glacier will be melting, and all these are components of the Earth. Then we need to know components about Singapore, the landscape. So we know it will be a lot of data, complex data. We feed it in, and we let the components interact and fast forward in time, right? So we can fast forward decades of time in the matter of depends on the complexity. If it's a simple one, maybe and with high enough speed computer, we can do it in an hour. If not, then a few days. But that's still way shorter than several decades of actual real time. So that will be time saving and allow us to plan better. So in that sense, it's not about forecasting. I know some of you are thinking, right? Isn't that forecasting? And there is whole set of theories on forecasting. Those set of time series forecasting and other forecasting, qualitative forecasting techniques, their results are typically the results are impactful but shorter. I want to say simpler, but of course the answer whether Singapore will be submerged, will not be submerged, that's a very serious answer, right? And if it's said by a respectable expert, then it's a very high quality, serious answer, and we should treat that very carefully. So it's not a simple answer, but simple in the sense that it's short, right? It's human computable. We can utter it out by human. What do I mean by that? We cannot say 1 million numbers in 1 second. That will be not utterable in what I'm trying to say, right? So utterable, we can say it. Human utterable answers will be that. Okay, in a sentence, let's summarize. Yeah, Singapore, about 20% of Singapore's coastal area will be submerged as Singapore. So that's possible, right? And can be comprehended by other people, other humans. But to generate 1 gigabyte of data and say it out in 1 second, like how computers do it and generating a gigabyte file in a second, We cannot do that. Or to visualize a gigabyte file of imaging data in a second, right? So computers can do that very comfortably. So impossible will be like seeing the black hole. I'm sure you have heard of that, right? Black holes are now so commonplace because it's no longer a myth. It's no longer a guess by the best scientists. It's no longer arguing that because of this, black holes are inevitable. I'm sure is that. Okay, a very famous, respectable scientist says that, then we think maybe it's true, but no one has actually seen one. And how can you see a black hole when it's black? Think about that, right? Because it doesn't, it not only it's having the name black, it literally is not emitting light. You shine a flashlight at it, it doesn't reflect. So it's just black. So how do you see a black hole? And through simulation, and this is real, huh? Scientists actually seriously apply all the physics, right, known physics, right, about quantum physics, about theory of relativity, about gravity, gravitational forces, interactions, and everything that they know, right, and then let time run, right? Let it run, let the simulation run in the attempt to find how a black hole should look like if such an entity obeys all these known physical laws. And then out comes gradually, pixel by pixel, this picture. So again, such pictures couldn't really be produced by AI. See, that's the difference. And if AI were to generate a picture, like create a picture to show me how a black hole looks like, you won't trust it. It's just for fun, right? It will just think about, analyze black. Typically, people refer to black. A hole typically is circular in nature, so it tries to draw a black hole, just a circular darkness. But turns out a seriously uh, produced simulated black hole picture based on collected radiation data, sample data from the universe, all known physics laws, everything. The scientists simulated this realistic image of how a black hole should look like. And fair enough, there is a central darkness gradually fuzzing out into some rims of aura, lights, and all that. And the fact that it emits lights outside the ring of the black hole, it's rather peculiar, right? So, and it's a kind of a computer outcome that nobody expected. And fair enough, it did show those. And so, and I'm glad I talked about this example, even though it's not really business, but it's the business of scientists, so it's still business, right? And it clearly distinguishes the visualization because we just look, simulation because it produces the right data, okay, not and comparing, contrasting it with AI produced image, which is sounding right in human terms, but not correct. Almost for sure it's not correct because AI couldn't comb through the internet for real looking black holes because none existed. Okay, so it's like impossible to see the black hole. So we may have what we call artist impression, right? So that's what humans think without following the laws of physics. So what makes this black hole also a dark patch, circular dark patch with a bit of light in the ring? What makes this picture, this black hole picture, produced by scientists using simulation, so different in the black hole picture produced by AI or produced by visualizer? It's because of the reliability, right? The belief, the reliability, that the accuracy is that we can trust that this is the real black hole, not just somebody's imagination. That is the solid quality that simulated results produce. And that's what we expect from simulation. Not some kind of show me how you'll be. Show me what the data looks like. So that's visualization, right? Give me a sort of you know, a artist impression of how Mars would look like. So AI can generate that. Simulation cannot because we don't have sufficient knowledge, the component knowledge about Mars. See, that's the distinct contrast between them. If you just want to have some sort of mental tinkling using a visual image, AI can do that, right? Even using a video. But we can just kind of watch and in a way forget, right? Because it's okay, maybe it's for entertainment. Hey, that's so cute, right? Uh, draw a fluffy cat video, right? So AI can do that to make us laugh. That's good. I mean, there's some emotional value. Can we trust that a fluffy cat would look like that? Well, maybe none exists on Earth, right? Uh, you know, generate a video of a frog-looking cat. And everyone knows it's going to be for fun and entertainment. And we know it's not animal cruelty because it's just digitally generated. Simulation, impossible to produce that. In fact, the answer that comes out should be calculation terminated, right? Because you couldn't solve all the known components of animal behaviors, DNA, whatnot, right? That it just cannot be produced. So if simulation answers that, then we know that such kind of combined animal can never be produced. And we can dare say that as a matter of fact, even though there's no such fact. Right? So simulation gives us that confidence to say it's a matter of fact that frog-looking cat cannot happen. Then if you use AI to produce one, we laugh at it. Yeah, this looks so real, but we all know it can happen. So that gives us the confidence. And that's very important because simulation, AI, visualization, very different stuff. Okay. All right. Next, I'm just going to list out a few points, a few pointers, that's all, right? So typically, such problems are easier to forward calculate than to solve. Like make x, so y equals to 2x. Now make x the subject of y. So we all know it's 1/2 of x equals to 1/2 of y. So we can reverse solve for x if we know y, right? So suppose the rule governing x and y is that y equals to 2 times x. Okay, so whenever we know x, we can know y. If x is 1, we get 2. If x is 2, we get 4. So now it's the reverse. Suppose I can measure y, but I want to know x. This is the reverse problem. And we can reverse solve it using algebra because everyone knows that, right? So x equals to half y. So now you can feed y the values. We know the values of x. That doesn't fall into this category. Okay. Those that fall into this category typically are those that are very complex in nature, right? We can calculate forward, very easy to understand. For example, calculate the probability density function of normal bell curve when z equals to 2, when z equals to 1. Okay, we plug in. It's rather scary looking, the probability density function, but we can just forward calculate it. It's exponential, that's it, right? Now find the reverse. Given that the PDF is this number, give me the value of z. Wow. Okay. First of all, for the whole z, there will be 2 numbers that will match that given height. And secondly, it's not so easy, right? So, of course, if your math is super good, you may try. But then typically what we do is we numerically solve it, right? So using what we call Monte Carlo method, which is in a way one-dimensional simulation. That means we're trying to find one number. We're not trying to find one picture. We're not trying to find one set of tuning parameters. We're not trying to find a collection of pixels that give the black hole picture, right? So the picture itself is the solution. So now our solution is one number. So it's like one-dimensional simulation. When it comes to simulation, then it becomes way easier. Right? So reverse solve algebraically very difficult, but simulation makes it a lot easier. Because simulation involves only forward calculation. Sort of like a massive guess and check in some sense. Okay. we'll see that later on as we talk about the methodology. Okay, easier to define than analyze or solve. All right, so that's whether in mathematical rules and formulas or human rules and formulas, because ultimately we'll convert or describe human rules and formulas to in mathematical terms again, right? So it's easier to define. And of course, we do that all the time, right? Don't do this, don't do that. And we can say those rules, but what do you mean by don't do, right? Don't do this. Whenever you try to do, you stop yourself. Okay, so don't do this, don't do that. How do you analyze such a thing? Whether this will help in your study, this will help in your health, this will help in your don't do, don't. So how do you like analyze it or solve it? But simulation a lot easier because simulation only tries to do it, right? And then you can prevent the code from doing it by stopping it. And then you gather the systemic behavior. Ultimately, if you don't do so many times, right, millions of times, 10 millions of times, does it help in achieving better health, better sleep, better GPA, better whatnot, right? So then situations where simulations are useful often have these characteristics as well, easier to describe. Right? They are often easier to describe the rules and constraints. Constraints are basically limits or requirements, right? Constraints, than data and content. It's difficult or expensive to gather the real life data and content. Okay, but way easier to just define the boundaries. Okay, so I can define the boundaries, but I'm unable to sample the data. I know the data's limits here, right? But very hard to measure the data itself, something like that. So if that's the case, then how to solve it? We don't even have a formula or theory about the data and the content, right? Because it's very hard to measure. Then what do? Well, we can at least get an approximate silhouette, an approximate outline of where the solution can be, or maybe even the actual solution itself through simulation. So that's another area. And then, of course, easier to construct. To construct, assemble, integrate from components, than to make a monolithic system. Monolithic system in the sense that we just have the system as a whole. So if you look at one building, then the building is one system. If you look at it as a component, then it will be part of a bigger system. That means if you're studying whether there will be floods in Singapore, then of course you can look at one building, right? It's complicated, but you can look at one building as one component, almost like a Lego block. One brick is one building, right? But if you're studying whether the building will collapse or not, then you want to talk about maybe the precast, prefabricated units of a room, a toilet, a living room, the connecting beams, the physics of them, the physics of connecting them together, how sticky they are, right? How easily break apart can they be, and all that stuff. You describe the components. If it is easier to describe the components than to just directly measure or estimate or have a formula to talk about the whole building, right? Then we should use simulation. For example, if there's a formula that says, oh, if the building is this height, this wide, this number of stories, this density, so many, many parameters, right? Like a big, huge formula that has 30 parameters, and that's too few, perhaps. Right? So that has 30 parameters. Is it for commercial use and estimated traffic density per day and all that stuff, right? So you have all that numbers that will be filled into these 30 variables, and run that formula. On the left side is the probability of collapse during a Richter scale 5 earthquake, let's say. So Richter scale 4, you have another formula, and 3 and 4, doesn't matter. If you can withstand 5, then 4, 3, 2, 1 is fine, right? So you have this 30 variable. I'm not going to do that because it doesn't exist, nor do I know it exists, and this 30 variable formula. You put it in, and out comes the probability, one number, right? So this will be what I describe as a monolithic system. This one big bang approach, you enter 30 numbers about this building, and I can tell you the probability. Okay, that would be nice. If you have, it's always good. So a formula is always some sort of a monolithic system of an integrated set of smaller components. Right? So a formula is always nice. No matter how complicated it is, you just plug in the parameters, the numbers, out comes the required result. Very good. Efficient, fast, very clearly defined. But how does this formula look like? So we all want to know this monolithic formula to quickly calculate the probability of this building collapsing, or any building collapsing, right? Because it will be a monolithic formula for any kind of building. If you, so long as you enter the height, number of floors, density, whatnot, right? It will tell you the probability of it collapsing at Richter scale 5 or below. Okay. But we don't know how to come up with that, right? Don't know. So not easy to do that. But it's way easier to input slowly, perhaps, right? To test out gradually the prefab rooms and living rooms and toilets strength, right? The, how they are being connected together, the physics governing all the physical movement of the prefab units and the whole building and everything. They are by no means easy, also involves a lot of work, but we know how to do them accurately. We know that all these are backed up by engineering rules, physics laws, right? Years of civil construction experience, knowledge about the soil, everything, and the wind and the pushing and the forces and what, we know that. We have all the data. But then how to use all that data to come up with one formula? Nobody can prove it. And even if someone comes up with it, can you trust that? Because there's no physical law or mathematical reasoning to back that up. Someone comes up with this formula, will you trust it? First thing you ask is, where do you get this formula? Oh, I just think from my experience, it should look like that. Now, would you trust this engineer's words? I mean, no disrespect to this engineer, but even if it is really out of goodwill, this formula is a very serious formula, right? Because if it produces the wrong probability, leading the management to do the wrong decision, then a lot of damages can happen. So, there's this lack of confidence or reliability. But when we can describe all the components, again, I'm not trying to say this is easy way out. They are individually easier to do. Individually easier to verify the correctness. Okay, this tested correct. Okay, next, let's test the implementation of gravitational pull on the building. Okay, let's try it out. We can test that separately and independently of the rest. Then let's say now everything has been tested. We run the whole system, right? And then we shake under Richter scale 5. And this time round, the building collapsed. Another time, the building stays. So the way we go is, to get the probability, we count over count. We do 1,000,000 times and we count the number of times of the scenarios in which the building collapsed. So let's say it's 5 times out of 1,000,000 times. So then it will be 5 over 1,000,000. That will be the probability that we get, right? That means 0.0000005 zeros, right? And then a 5, right? So is that good or bad? Then that will be up to the panel of discussion. But at least that's a very reliable probability that is now entering into discussion. Okay, perhaps the real answer is 0.0000 with 5 zeros in front, 624. Okay, so we underestimated. Right, our guess was 5, it's actually 624. Or 500, 500 is actually 624. So we underestimated. But close enough? Yes. If you're not very sure, right, so the panel may say, oh, only 1,000,000 times? Can you run 100,000,000 times? Oh, that will take 10 days. We can wait, because it's a very serious decision. Let's wait 10 days. Or it will take 1 month. Oh, okay. Can we run on 10 computers, right? Each one running 10,000,000 times, because they are running simultaneously, right? So now it will take a day. So then what happens is 10 computers running 10,000,000 times, we can take the counts and add them because it's distributable. So that's another very nice tactical advantage of simulation. I haven't touched on that yet, but it's like you can let different systems simultaneously in real time simulate, right, many trials, and then you add up the numerators and the denominators. All the crashes you add together, number of times, 10,000,000 plus 10,000,000 times 10, right? So 100,000,000 times. So all the crashes add together. Oh, now is 621. Oh, okay. Actually higher than 500, right? See? Okay, so now, but with 100,000,000 times, you get 621. That means 0.0050 zeros and then 621, right? Then again, the panel can now discuss whether it's high or too low. No, too low, right? Too high. So if it's too high, then they might want to change the design, the structure, the whatnot, reinforce whatnot, right? But whatever it is, the reason why they reacted on the 621 when actual number is what, 625 or something, we don't know. We will never know. We will never know, right? But then the 621 comes so close that we dare to trust and make decision on it. If we say 621, that's higher than 600 by our building standard. So let's do something, right? So in that sense, we gain a better fee. And then it will be documented so that if somebody says, no, then changing it will drag us back another 2 months, we have to pay liquidated damages to the customer. No, we cannot, right? So let's go ahead and this will be documented, right? So if something should happen and the building collapses or partially collapses, then you can dig back and see if, proper guidance have been used, have been proper care have been taken, right, in the management to ensure that all the rules and safety are conformed. So whatever is the case, these are, in some ways, different ways to describe the same thing. That it is the systemic, the collective, the overall output that we want to know. Okay, the output can be one number, can be a set of numbers, can be massive number of numbers like a picture, right? Every pixel will be 3 numbers, RGB. So 10 mega times 3, right? So 10 megapixel of numbers, that's a picture, or 10 seconds, right? Or simulate the movement of galaxy. Simulate, not visualize the movement of galaxy. So we from all the astronomical data we gather, we know that Andromeda Galaxy and our Milky Way, they're heading towards each other. How do we know that they were heading towards each other, right? That they are moving. So if they move slightly over our very short, 1 decade of observance of the stars and the galaxies, right? if it's so minor, even minor movement in astronomical terms will be millions of kilometers. That's like very tiny movement, right? So minor movements can be registered, and then we say, okay, with that limited data, kind of like extrapolate. But we are not forecasting. We are forecasting. We are like forwarding in time, right? But for the galaxies to collide, that may take like certain number of years. We like to know how many years. Okay, so now let's simulate. So simulate based on the gradient of movements and trajectory. Would it miss each other? Maybe in 3D they look like they're coming close, but they actually miss each other. Will they come close enough that they start accelerating and start to crash faster and faster, right? So it's actually shorter than we think. Theoretically, the prediction is 100 billion years, but we forgot that they accelerate towards each other. Okay, so then it will be much shorter, right? So when we simulate, all these will be taken into account, galaxy by galaxy, star by star, planet by planet, and then picture by picture, we can see the generation of that. Because all we want to know is how long does it take to collide, if they collide. That's just one number. But of course, we can also see it. So simulation can also produce the movements, additionally produce the movements in order to know how long it takes. And then the movement data can be recorded and played back. That's visualization. So number of years, maybe 30 billion years, right? So then we can now write an article about that to warn the mankind that in 30 billion years we no longer will be in existence. Okay, so that again will satisfy all these criteria. We know the components very well. We can describe them. Importantly is very well means cheaply, efficiently, and very importantly, accurate. Cheaply must be low cost, right? It will be very costly. Don't get me wrong. It will be very costly. To write a game will be multiple millions of dollars of endeavor, right? To do a reliable CAD/CAM software that sells at very high license price is not because of paying the software engineers and the firm and whatnot. It's to test the reliability, right? So underneath those serious simulation software is a very serious effort to implement reality one-to-one. If in real life you can do it in this way, governed by physical law and mathematical rules, then in the simulation, it will do it this way. If in real life you cannot proceed, then you cannot proceed. If in real life it explodes, then it explodes. So that what you get in simulation is real life. That is the quality that comes over from serious implementation. So from here on, of course, I will always be talking about serious, right? So systemic behavior is what we want to know when we can describe the components accurately, cheaply, right, and efficiently. It doesn't take a lot of time. So we can then further recognize such situations when we encounter these rather equivalent but not actually entirely overlapping characteristics. Okay, so in what follows, we will examine the core part of doing simulation, which is to have probability distribution, giving rise to the notion of cumulative distribution function. And then what we are after is the inverse cumulative distribution function. And then using the inverse cumulative distribution function, we want to generate random numbers. This is the core of all simulation software. I say software, but what we are doing is this whole methodology of simulation, which in contemporary terms, ultimately we'll always rely on computing, right? And to do that, you have to have software. So simulation software, whatever you talk about in all these applications, must be able to generate random numbers in a way that is dictated by the required governing rules and laws, like laws of physics, laws of society laws, right? Like 20 people do not live comfortably in a 100 square meter house. Sorry, 100 square meter, yeah, 100 square meter house, right? Uh, physically, yes. So physical law, yes, but socially, not permitted. Legally, not permitted. Socially, not uh, quite doable, right? So we will also simulate that. So we will also implement legal laws, rules, right? So if I randomly throw cigarette butts on the streets, right? In Singapore, if you just do that, you can be fined $500 or more, and multiple times you may even be put in jail. So if I do that, right, what's the chance of getting caught? And then what happens if a recalcitrant smoker does that? Especially when I saw that drivers on the roads, right, when they finish, they just threw it away, right? So, hey, nobody caught me, so I will do that next time, next time, next time. So let's try to simulate, right? So, what's the probability of getting caught? What's the impact, the damage, the fine when you do get caught? So these are not physical laws. These are not mathematical laws. They are social rules, legal law, the law, legal law, right? The actual law. So we can implement that. And why do you fine $500, not $550? Because the law says. But then the judge may move it up because the law says at least $500. So the judge may say $600 or $1,000 because you're doing it second time. Whatever it is, we can also mimic the randomness of the judge's ultimate judgment, the final fine that this recalcitrant driver will have to pay. So we need to generate random numbers, right, in a way that follows the distribution of the applicable rule. Basically, is to say that we change the Q constant into rand. This is the part where computer science marries mathematics. This is mathematics, this is computer science. Okay, so essentially, I think that is the next 2 points. Okay, so I will also try to illustrate that the effect of generating random numbers. I mean, you can actually solve problems using generated random numbers. First of all, it's generated. Second, is random. So they seem to be ironical and contradicting each other, right? That you can generate, that means you know what's going to come, and it's random in nature. Can that really solve problems? So that's one thing I want to illustrate from a simple example of calculating the constant pi, and I will show you how we can do that. Don't worry, it won't be a lot of manual writing, right? So it should be something that will be illustrative. But first of all, what is probability? Well, we study probability. We know that it is a histogram essentially, right? So probability of what is going to happen can be described by setting x equals to that point on the x-axis and finding the y value. So what we can do is that we can start by having a uniform distribution. So a uniform distribution will look like this. All right. And without loss of generality, let me just call it A and B. And my uniform will have a probability density of constant. So uniform here, I'm referring to continuous uniform. Okay. So in this case, the CDF of a value x is basically the sum or the integration of all the probabilities less than or equal to x. And this equal to is important, particularly in discrete case. So the definition does include the equal sign. In the continuous case, equal or not equal is not so critical because the probability of the random variable equal to any constant is the area from the constant to the constant, which is 0. But then for discrete, then it will be meeting. There will be some non-zero probability. So we've got to take care of that as well. So the CDF is this, right? And of course, the inverse CDF will be that the CDF of something gives rise, let's call it Q, right? So this is the Q, the value, right? And because Q is going to be a number that is the sum of probabilities on the left tail in the sense. So this definition is left tail. We could have defined it as right tail, but everyone in the world talks about left tail, so please don't be the outlier to talk about the other way around. So Q is the sum of all probabilities on the left tail of X. And that number itself cannot exceed 1. So itself, Q, is a number between 0 to 1. And what we want to say is that if I know Q, all right, and Q is a number between 0 to 1, if I know Q, find me the value for the CDF. That means that value, if when I feed it into CDF, I get Q. But I now know Q. For example, Q is 0.2. I just don't know what is the value, the parameter in the CDF function that gives rise to Q. So this is the purpose and function of inverse CDF. So we can find out this question mark by applying inverse CDF onto the input value Q. All right. So CDF, think of it as area because it is the probability of everything less than n. And probability on the continuous curve is the area. So think of it as the area, right? And x is going to be the point on the x-axis, and q is going to be the area as well. All right, area. And x here, point on x-axis. Okay. And for inverse CDF, it will be that we input the area. So because Q is equal to area, right? So this will be area. And this would be point on x-axis. So we get the reverse. That's why it's called inverse. So if I apply CDF onto inverse CDF of Q, right, I get back Q. If I apply inverse CDF to CDF of X, I get back X. So that's the way it goes. But that's this the mathematical behavior is not what we are after. We are after what it can do, right? What this CDF and InvCdf can do for us. And what we then want to illustrate is for several different distributions, the way it looks will be something like this. So this is 1, this is 0, right? So the CDF curve will rise, rather let me just add with a hint of orange. And touches 1 when it touches. So because it's a straight line, because it's keep on adding constant amount, therefore the gradient is also constant, and so it's a line. And it will reach 1 because the whole area under the curve must be 1. So it will reach 1 when it reaches B. And from here on, it's always 1. It's always 1. So you can extend it a little bit by saying that if you insist, I'm be adding no more, right? No more probabilities after B. So it will always stay at 1. Okay, next we can look at exponential curve, just to have a different feel of what's going on. All right, so exponential curve, we can talk about the lambda here. It falls steeply exponentially, only touching 0 at infinity. And this curve is exponential. Okay, and what happens is that interestingly, exponential curve has a CDF that is also exponential in nature. Starts with oh, I mentioned exponential too quickly. It is exponential, but the other way around. Okay. Because the CDF always starts from 0. Okay, so when I drew it, it started from somewhere high up there. Clearly not from 0. Y equals to 0 because y-axis is the CDF. And it starts from 0, and then it rises to 1 as the not time but the values of x increases into infinity, and gradually touching 1. That means adding lesser and lesser probability to CDF, finally adding 0 probability to CDF, right? So finally touching 1, ultimately at infinity. So something like starting from 0, at first rising very steeply, then as x increases, it tries to reach 1, but never quite touching 1, but only arrives at 1 at infinity, something like that. Right? So now it looks a lot more correct, but it is also exponential in nature. So it is like the point of diminishing return kind of curve. All right, so you can keep on doing more and more work, spend more and more time, spend more and more money, but the increment is infinitesimal. So the last bit, the 99.99999, the 0.0001% of improvement is always very difficult in that sense. Okay, we of course must talk about normal distribution, right? And this will be the mu Okay, and centered at mu. And the CDF is going to look like centered at mu as well. And there is also a sense of 0 and 1 because CDF is always centered, going from 0 to 1. And when it reaches mu, the CDF of normal distribution will have accumulated half, right, 0.5 of the area. So 0.5 is the sort of turning point, because after that it will grow towards 1 like this, and before that it was trying to reach 0.5, rising quickly towards 0.5. So it's very much like an S curve. Okay, very much like an S curve. And let's label this. This is our normal curve. Okay, and that's about it. These are the commonly encountered ones. Of course, we have others, but you can begin to get a sense of how CDF behaves. And one more, of course, one more illustration, I would say, that's more looking like a Poisson distribution, but can of course be understood as any other discrete probability distribution. That means any distribution. So it can be here, 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 then this, and keeps on dropping. Can end in the finite way, or it can just go on to infinity. To infinity in that sense. So again, I mentioned the ink smudged, so I better not use the ruler. Okay, I mentioned this before. The actual discrete distribution only requires this point to denote the height, because it will be 0, 1, 2, 3, 4, and so on. So because it's undefined between 0 to 1, 1 to 2. But for visual ease of viewing, and again, that's visualization, we draw a horizontal line, sometimes with a vertical line to make it bar-like, vertical bar-like. But again, that is just for illustration rather than a necessary part of the drawing. And for CDF, we see that at 0, 1, 2, 3, 4, 5, we will accumulate chunks of probability as defined by the height of the discrete diagram. Yeah. So at 0, we accumulated less than equal to, remember, less than equal to. So at 0, we would have accumulated the height here only. So the height here, I'm going to suppress it a little bit. Okay. Then we have a 1, which adds a chunk, a vertical chunk, so it rises. Then 2, it adds some more, it rises some more. Then, okay, I guess I want to align with the ones on the left side. So then I got to start from a lower base. So, okay, make sure you can see. So here it goes to here, then we increase by a bigger chunk, then we increase some more, then we increase a lot lesser, then a lot lesser, then a lot lesser, and so on. Okay, so it's kind of like a discrete discrete dots that try to reach 1. If this sequence of dots go to infinity and they add up to 1, then this sequence of dots will finally touch 1 here when we go to infinity. Right? So again, for illustration, I'm just going to embolden the dots a little bit more for visual ease of viewing, but it's a single point. All right, now these are the CDF. Okay, the inverse CDF is basically like you flip the, you kind of flip the x and y axis. So the y axis becomes x axis, x becomes the y axis, because we're trying to make x the subject of y, the other way around, right? So we don't have to redraw the diagrams, but we can now just look at the Q here, right? So this is the Q here. Okay. So the Q here will basically be a number between 0 to 1, yeah? Because that's the value. So the value itself is the area in the PDF. So on top here, the axis is PDF, probability density function for continuous distributions, and this is the probabilities. Okay, and this Q, if we are given a Q, because when we are solving for inverse CDF, we are given a Q. This number has to be between 0 to 1, otherwise it won't make sense. So let's say I have 0.5. Then I will move vertically to 0.5, and so my okay, so I would then move vertically, right? So this is the inverse CDF arrow. And then dropping to the bottom, and this is my inverse CDF result. This point here, which is likely to be A plus B over 2. Right? That means the midpoint between A plus, which is true, right? Okay, so hopefully from the table lookup, the CDF picture lookup, you can see the mechanics, the action, the finding, calculating inverse CDF in action. It can be a complex function, inverse CDF itself, to describe this shining a beam of laser from the y-axis given the height, given the Q value, and then reflecting it down to the x-axis to find that value on the x-axis. This mechanical action is very visually simple. You just shine a laser beam, very sharp, accurately defined beam, touching on the, once it touches the orange CDF curve, you reflect 90 degrees downwards. That will be the inverse CDF value. So the thinking is very simple. To describe inverse CDF, however, may result in humongous mathematical formula. In the case of exponential, very easy one. That's why I put it in here. Uniform is also easy because it's linear, right? Normal will be not quite possible. And the only way to do it is what we call numerical approximation methods. Okay, so we do that using software. That can be calculated very quickly. In a way, it's a well-known contextual numeric one-dimensional simulation. So it can be sort of optimized in the software sense to do table lookup and then fine-tuning it with error correction and all that. Then we can get the value very quickly. So numerical approximation techniques, they are very well understood, coupled with computing performance enhancements. The calculation of inverse CDF, even though the mathematical formula is super complicated, it's very fast. For discrete inverse CDF, it is also table lookup. So we find a place, right? And there may be a gap, right? Then there may be a gap. So we can take 0 or 1. If we take 0 or 1, we have to test if it satisfies the CDF definition. So let's come to that in a while. Huh? Meantime, let's just simulate a few more. Our inverse CDF. So our Q can be here. And then the inverse CDF is based on the vertical height. Right? So if we do it here, Q, then our inverse CDF is a positive number. If we do with Q below 0.5, our inverse CDF will result in a negative number if we use the standard normal, right? So mu is 0. Okay. Now what happens when we do it on a discrete distribution? So discrete distribution, I was saying, suppose our Q is 0.4, right? Somewhere here. Well, if it is exactly, let's say 0.1 here. 0.1. So for 0.1, right, we will shine and it will hit the orange dot and we'll get 0 exactly, correct or not? So that part is not very difficult. But suppose our Q, I won't use between 0 and 1 because it's too squeezed. Maybe 1 and 2. So suppose our Q is somewhere, here. That would end up resulting in pointing at a gap. And I think the chance of pointing at a gap is going to be very high, right? Because the dots will need exactness to be hit upon, but the gaps are like so wide open. So if we choose 1 versus we choose 2, we cannot randomly pick. We also don't take the average. We don't try to return 1.5 because that would make no sense in the domain of the x. So we're going to say CDF of 1.5. That's 0, right? So we cannot return 0. So which one is correct, 1 or 2? So we check for, now suppose this is 0.6. Okay, suppose our Q is 0.6. If we take CDF of 1, CDF of 1 will be probability of x less than or equal to 1. That is not really Q, right? Not really Q. Let me move my picture here so that I don't block. If Q were 0.6, then we take CDF of 1, maybe that's 0.55, right? So that's not really Q, but it doesn't exceed Q. If we take CDF 2, then it will be more than 0.6, right? So it may be 0.668, 0.68. And probability of x less than or equal to 2 is going to be 0.7, larger, right? So if we say probability of x less than or equal to 2, Q is 0.6. This is 0. Let's say 0.5, 0.6, 0.7. So probability of x equals to 2 is 0.7. Probability of the values of x, if you look at the probability histogram up here, right? Probability of x less than or equal to 2 is actually 0.7. So if we do that, well, that's exceeding the Q already, right? So we won't do that. We will end up using the 1 value here. So we can think of it as the 2 having a wall here, blocking it, right? So that it will fall back. So the Q beam will hit upon the wall and drop to 1. So So 1 is our inverse CDF value. Okay. And that essentially is how we will be able to compute for all the distributions having a CDF curve, even for discrete case, right? So we just need to adjust for some non-existent Q values, right? Given discrete case, the Q values are also discrete. Certain numbers of Q values exist only. But we would like to also kind of like extend the definition for non-existent Qs to also fall back on existing values of X. And that is the definition for, in some sense, modified or extended definition for the inverse CDF of Q. Okay, so now that we understand the inverse CDF function, then essentially this is not yet, this is not yet simulation. So to simulate, we perform inverse CDF of the rand function. So the rand function is the rand function, any computer, any software, any library will have this function. It may be called just rand. It may be in Excel it's called rand, just rand itself. No parameters. You just keep calling it. It'll be a number between uniformly distributed between 0 to 1. Okay, with many decimal places. So example will be 0 0.1234567, 0 0.3345, and all that. A lot of numbers. You keep running the same function, it will produce different number all the time. No matter how quickly you call. The second time you call is different. The third time you call is different. Okay. So this rand function is always implemented in all computers. Sometimes the rand function itself is implemented as a simulation table. So the rand function is a table lookup of pre-computed random numbers. Why? Because that's for generating stable sequences of random numbers. So we want to test simulation software. How do we test? When every time is different, right? So this time around, you test the building collapse. I want to reproduce this collapse in my debugging of the software. How do I do that? And because the second time I run, all the random numbers will be different. So this time the building didn't collapse, right? And remember I was saying like 5 times out of 1,000,000 times. So it would be super hard to encounter the collapse. So we want to like fix the random number. And there will be this pseudo-random number sequence where the numbers will be generated repeatedly. They look random, but every time you reset and run again, the same sequence of random numbers will come up. So that's nice. But anyway, that's just to let you know that in case you observe this miracle, that you observe the same sequence of random numbers coming out, it's purpose built to be so. So don't be alarmed. But if we use the native rand function, it will be truly random, right? So this truly random is very random. Means that if you run rand 100 million times and you plot the histogram, it will be a perfect, smooth rectangle. Okay, perfectly smooth rectangle, uniformly distributed between 0 to 1, fixed. And with that, what we do is the InvCdf will treat this rand number as Q. All right, so we treat as Q. Treated as if it is the CDF value piped into InvCdf, and InvCdf will map it to the relevant feasible range for the x, like between a to b for uniform, between 0 to infinity for exponential, and so on. So that we will get a number or a sequence of numbers on the x-axis that is valid for the value of x. If it's discrete, we will always get 0, 1, 2, 3, 4, 5. We will never get 6. We will never get -5. That kind of meaning. So that when we feed these sequences of numbers into downstream software modules, then they will start to use that number to mimic, right, various physical events or imagined events, such as tidal waves height. It's always some height, not infinite height, not 1 millimeter, but some height, right? Like we need to describe this height, and it's random, and it's between let's say 10 cm to 10 meters or 100 meters. But the 100-meter tall tidal wave is a lot rarer than 10-meter tall tidal wave, which itself is also very rare, much rarer than a 1-meter tidal wave, much rarer than a 50 cm tidal wave and so on. Right? So we need to understand the distribution of the height of the tidal wave, and then we can describe, okay, in this run, the tidal wave is, throw a dice, InvCdf, get a height, 1.2 meters high. Oh, okay, fine, it won't affect our coastal buildings. Right? Second run, and so on and so forth. So we keep throwing a dice, I call it throwing a dice. A dice here is not 1 to 6, but 0 to 1, with infinite number of possibilities between them. So all the creativity from computers, from AI, from everything come from decimal places between 0 to 1. That's all. In a way, that's quite true philosophically and theoretically. Right? So you can think of InvCdf as a magnifier. It changes or transforming the number, the decimal place number, 0 to 1, into the sort of reality number in terms of meters, in terms of kilograms, in terms of Newton forces, in terms of earthquake Richter scale. Oh, now there's an earthquake. What scale is it? What Richter scale is it? Throw a dice from 1 to 10. So that kind of thing. And we know that Richter scale, smaller Richter scale earthquakes are more frequent than, so it cannot be uniform distribution. It probably cannot, it probably looks like exponential, but this may be too frequent, right? Richter scale 1 may be some frequency, Richter scale 2 and 3, maybe they are more frequent. Then Richter scale 4, 5, 6, they kind of fall off in terms of occurrence probabilities very rapidly, something like that. So again, we need to gather data from real life, then we can describe it realistically, seriously, and accurately to the computer, which will just mechanically do this lookup to find the InvCdf. So throw a dice, find the InvCdf to map back to reality, and then produce the resulting damage or consequences or profitability for your business, for example, and then we measure the overall macro behavior. Remember, this is just one throw. If we throw it 1,000,000 times, all these calculations can be done by also GPU, right? So we can do this 1,000,000 calculations very rapidly, and then try to magnify and sort of forward animate the consequences. It can be good consequence, it can be bad consequence, whatever the rules of the reality, social order, legal laws apply, right? So that's the whole spirit behind simulation. All simulators will perform this, and massively many number of such calculations. So in order to come up with one result, and then we repeat that calculation again several million times in order to come up with some sort of distribution of outcomes. Okay, so like 1,000,000 times, 5 times computing will collapse. That kind of distribution of outcomes, and we can then calculate the probabilities in the sense of empirical probabilities. So we don't have a formula to describe the systemic behavior, but we will have a distribution of possible outcomes. And then we can judge, we can assess the damage, we can do various discussions, planning, strategy over those outcomes. Okay. Let's just quickly do a one-dimensional simulation. Okay, so because 1D is a lot easier to understand and imagine. I have to show you this because it should be helpful to understand how the distribution works, right, in terms of helping us to know the reality. Now, if you are watching this video, you probably would have already studied the various videos and topics in earlier sessions of ST118. Okay. What we can do is to revisit one example where we say example, right? So we say we want to know the systemic output. What's the systemic output? The population me. Okay, we want to know this, but we couldn't know. Correct now, yeah. So we couldn't know. So no choice. We have to sample and perform various statistical techniques like confidence intervals and hypothesis tests, right, to find. But here, suppose just by describing this thinking, we suppose that, let's say, mu equals to 0.7. But we don't know, right? Okay. So the way simulation works is to start by saying we know nothing about reality. And this means that we're going to have a diagram, right, that looks like this. I'm going to lift up my ruler. Okay. And we have a box here. Okay, so this is 0, this is 1. Okay. And we know nothing means we have uniform distribution. Know nothing means uniform distribution between 0 to 1. Sort of like the rand function itself. Okay. Because knowing nothing means all possible numbers are likely, and there is no reason why we should suspect that the mean is closer to 0 or closer to 1, because we know nothing. We just started, right? We haven't even sampled. We know nothing. So if you ask me what is the value of mu, and notice that my x-axis is the value of mu. That means what do we think is the chance of mu being 0, being 0.1, being 0.2, being 0.3, being 1. Let's say we limit the range to 0 and 1. Or it can be 0 to 5, 0 to 10, doesn't matter. So long as it's a fixed range, then we say, what's the chance of mu equal to that number? Well, they are equal in likelihood, correct or not? Yeah, so because we have no ground to say that mu is certain value or closer or larger than certain value. No. So it's going to be uniform. So what we do is we're going to start to sample, correct now? Now we're going to sample. And when we sample, we will obtain some data. Okay. And let's mark the accidentally hit the camera. Let's mark the correct answer with the pink dot here, right? And remember, we don't know this is the correct answer. So what we're going to do is we will sample and gather data, and we start to get some sort of rippling. As we gather data, we start to get ripples, right? Ripples to influence the knowledge, right? So that we now say that some values are more likely than others, although we cannot conclude that. And because of our sampling, depends on how much we touch the reality, right? We talked about this before. We will therefore update our distribution. Now remember, we are not updating our entire distribution from our set of sampling. The more we touch reality, the more we update our data. All right. So as we touch reality more and more, we start to get some guidance from the samples we gather. Of course, all these wriggles I just draw it by hand, but I'm trying to narrate to you how this entire activity of touching reality, sampling, measuring real life data affects the distribution, right? So once we gather more data, we will update our, we'll adjust our distribution. That's called updating our distribution. Remember, this is distribution of mu, okay, not x, the measurement that we are dealing with. For example, we are saying the tidal wave, on average, what's the average height of the tidal wave? 0.7 meters, right? So we are trying to measure that, and in a normal histogram, we will be talking about the various measurements of the tidal waves. But here I'm talking about the mean itself, the actual mean itself. Okay, so again, doing this marker, as we gather more and more, and of course, I hope you start to see that the shape is seriously now in favor of some value, not values, but some value. And in fact, it is also possible there's room to allow for bimodal distribution, right? So if there are two average tidal waves that seems to exist in the population, then yeah, it will show as a bimodal situation. But here, you can roughly guess what I'm trying to do here, right? Even though I'm manually and therefore subjectively drawing it, but I'm guided by the known behavior, right? Which is that as we gather more and more sample, with more and more knowledge, with more and more updates of our knowledge distribution of mu, right? Ultimately, we will get this situation. Right? So with a lot of sample size, we'll get this. And in a way, this is how AI also figures out what kind of picture, what kind of sample, even textual output is the right thing to say when we give it a prompt. So when we say, tell me a story that has happy ending, then what are we expecting, right? So it will say starts with no knowledge of what you want, then some knowledge, starts to figure out based on the weights of the trained neural networks. Oh, happy ending tends to have, people meeting together. So there's some translation going on there, right? So usually for a story, the number of people will not be more than 5, right? Because probability of characters beyond 4 is very, very small. And so let me try with 3. So, so something. And you want a short story. So let me limit to 2. And I must make sure these 2 people finally end up being together. So together is the mean outcome of happy story endings, let's say, right? Something like that. So in the case of infinite number of times, then we will end up getting exactly 0.7, right, with a fixed height, basically a bamboo stick, because it will be infinitesimally thin and having 100% probability on the 0.7 itself. So let me just quickly say that with more knowledge, right? With more knowledge, that is more samples from sampling, we get to update our probabilities distribution, right? So the updates are done how? Using, yes, Bayes theorem. So we have the prior probability, then with more samples, more data, we calculate the posterior. The posterior then become the prior again. With more data, we update to become posterior. Then the posterior becomes prior again and updates get posterior, and so on. Right. So if your sampling is random and unbiased and proper, you will eventually converge. And if of course mu actually exists, then you will eventually converge to this. Right? So with large n, then we get this. And with infinite n, we will get the ultimate. Yeah. So of course, we always terminate at some practical number of samples. So I just want to show you this simulation manually drawn, right? And just trying to show you how, you know, the knowledge can be built up, right, from sampling, from histogram, and then using, therefore, InvCdf and RAND, we'll be able to exploit such a distribution and then to sort of feed it into larger systems, right? So larger systems can be many of these, like for example, tidal waves, right? So tidal waves, we talk about a system of tidal waves, you know, reaching Singapore coast. So we want to study the coastal behavior. So it's no longer just one wave, but many waves, right? Hitting the coast over many parts of the coast, then running it through time. So that the whole system is like, you know, not only in area but volume also, and then in time. So 4-dimensional space. So that's just a quick sharing, right, of this thinking. Next, and the last part is what we are trying to do here is to talk about the example on calculating pi using simulation. Okay, some of you have learned how to analyze pi, you know, using various approximation techniques, numerical calculations, Taylor series, and all that stuff. So pi is a very interesting number. Let's say we are relearning this thing and we reset our brain. We saw this symbol, no idea what this number is, except it's a constant and it's very important. Okay. How do we determine the value of pi? That's our aim and mission now. But before I continue, there's a need to explain the whole so-called principle guiding it. Remember, we need to know our components well. So what is our component, right? So we are going to use simulation to calculate pi. So our outcome will be pi itself. Sometimes we do want to know pi, but we may not be able to sort of simulate it directly. What do you mean by simulating pi, right? So what we want to do is to use the concept of dart throwing. Okay, we're going to throw darts, or you can say shoot arrows, doesn't matter, right? We're going to throw darts at a particular board, and this board is going to be wait, let me write down first. Find pi using simulation, right? Okay, so the idea is we're going to use this idea of Monte Carlo simulation, which is that we will draw a board of a square. And I wanted to draw a large one to make it visible. Okay, so it's a square. I don't know why it looks like a rectangle on the video, but it looks like a square on my paper. And I'm going to inscribe. Okay, hopefully I do it nicely because I'm going to do it freehand. I'm going to inscribe a circle onto on the inside of this square. Okay. All right, I think this looks round enough. Pardon me if it doesn't look round enough on the video because it seems to be stretching it horizontally. All right, you guys see this circle, right? So this circle, if I say that the square has 1 unit, 1 unit in length, that means the area is 1. So we can safely say that, where's my safely say? We can safely say that the area of the square is going to be 1. Yeah, agree? And because of the way we constructed it, the radius r will be 0.5. I mean, this is necessarily true, right? And we can then say that the area of the circle is going to be equal to pi r squared, and that's going to be 0.5 times 0.5 times pi. So that's 0.25 pi. And we don't know what is pi, so we are unable to multiply it out. In fact, finding pi is our mission. So this much we learn from geometry, right? So mathematical rules and the geometrical construction is our governing law. So we don't have physics, we don't have reality. Our reality is this picture. That means we cannot be having an area of circle larger than the square because we have constructed it inside the square, correct or not? So we know that pi therefore cannot be larger than 4. Yeah, so that essentially is what we are going to say. That the area is done, and the ratio of the area of circle to the area of if I divide through to the area of the square is necessarily known and must follow from our derivation here. So it is going to be 0.25 pi. Has to be, right? No other way. It has to. And in other words, we know that the governing rule is going to be pi is calculated from 4 times of the area of circle divided by area of square. Okay, area of square is actually 1. We know that, right? But I'm going to just keep here because we're not trying to algebraically simplify it because no point, and we are unable to go anywhere, right? We'll be just going in circles. So why do I keep this when we kind of know that the area of square is 1? And the idea is that when we have this ratio here, okay, this ratio, first of all, we know area of square, but we don't know area of circle because we lack pi, so we can't calculate it. But this ratio can be simulated by throwing darts. Right? We're just going to throw darts randomly, closing our eyes. Right? We're going to throw darts randomly between 0 to 1 on the x-axis and 0 to 1 on the y-axis. So that means throw a dice, get a number between 0 to 1. That forms our x coordinate. Throw a dice between 0 to 1, and we take that number as our y coordinate. Right? So the only governing limits will be the 0 to 1. And because we have no knowledge, we're going to throw darts, right? Throw darts randomly at the board. Yeah, we're going to do that, and some darts will end up inside the circle. Some darts will go outside of circle but inside the square. And we will not have darts that go outside the square. Okay, so we throw darts randomly at square board, right? Some darts will be inside the circle. We will say that that is so darts inside circle. That's going to be our count of circle. Let's just do a symbol there for a quick notation, right? Count of circle. You can imagine that we can count this in program. Then darts inside square, outside circle. We can call it the count of the corners of the square. So I'm just going to color the corners. That means they are outside the circle, but inside the square. Okay, so that means the darts will be grouped into two parts. All right, so they are in these four corners or inside the circle. So that's going to be, so it's mutually exclusive. All darts will be in either one of these, right? And never in both, and always in one of these. So good. We assert that the count of the circle over count of square is going to approximate area of circle over area of square. Is that okay? Now you see why I want to keep the division by area of square, because we need to count the darts inside the square. And that basically is the sum of these two. So we're just going to say that the count of the square itself, count of number of darts inside the square, is actually just the sum of both, right? Count of those darts in the circle plus count of the darts in the corners. That has to be it. And we will just call that our simulation parameter n. How many darts? This is how many darts we throw. And all these can be tracked programmatically, right? So because we can throw a lot, we can throw very little. You throw little, you will get the answer very quickly, but it will be crude, very, very rough approximation. Okay. If you have large n, then you got to wait for a longer time, maybe go for a meal, then come back. But the answer might be much more pleasant, more decimal places. And so that will be our plan of attack, right? So right now, let's just imagine. You don't have to know any programming yet. Just think through the steps. And so long as every step can be easily translated to a programming, then we are done. So what we're going to do is we will set n to be, let's say, a number, say 10,000, right? And we'll throw 10,000 darts, simulate that by generating random x coordinates and y coordinates n times. So there'll be 10,000 x numbers, 10,000 y numbers. So together, each number in x and y will form a pair, which is a coordinate, which will be the sort of destination address, the ending location or spot that our dart will be placed on. So the 10,000 coordinates will refer to the 10,000 darts that land on it. Yeah. If the coordinates is inside the circle, right? So we will have, so each dot, we need to describe what is inside the circle, right? So each dot is simulated by xy coordinates. Well, mathematically, we'll write it as xi, yi, but every time I see a suffix, it becomes a bit more complicated, xi and yi. You know, there's like a lot of variables. So we just leave it as xy, but you know that we'll do this 10,000 times with 10,000 different numbers, right? All between 0 to 1, right? So a dot is inside circle if, right, if you recall, the circular equation is x squared plus y squared is less than 1. And it is outside otherwise. Now, of course, the equal case is debatable, but also not important. The chance of the dot landing on the parameter itself is nearly 0. All right, so we don't have to worry about that. You can try both ways if you like, but we'll just say less than 1. Okay, so it is programmatically, the dot is inside the circle and therefore goes into the count of circle if the coordinates satisfy this, right? Otherwise, outside the circle, but inside the square. That means otherwise it will go into the count of the corners. Okay, so this is going to be correct because every dot is either satisfying this or not satisfying this. So it's mutually exclusive. And all dots will be either inside the circle or outside the circle, but it will always be inside the square because by generation, we will limit, right? We will limit the x and y to follow uniform distribution between 0 to 1 so that it will never go to negative area, right? And never go outside the unit square. That's it. So how does this work? And once we get C of circle over C of square, we can replace that with this bracket. Right? So what the final part is that once we get good value of C of circle over C of square, right? We get pi equals to 4 times of C of circle over C of square. When we say good value means our n is large enough, right? And we have finished the calculation. If we have to wait 1 hour, we should get a good value of this. Okay, but we're not going to do 1 hour. Just trying to show you how we can do this experiment rather easily using Python. So let me just prepare a little bit, just a while. Okay, let me show the Python screen. I'm just going to run a few lines to be able to implement this. Let me keep the theory on the right screen available and move myself in here. Okay, and of course, to make it aesthetically nice, I'll extend the window a little bit. Okay. First, let's set our n to 10,000 so that the computation will be fast. 10,000 is a very, very small number compared to simulation, when in various simulation. And we're going to throw the dots. To throw the dots, I'm going to make use of a package called numpy because it has all the random numbers and is able to handle an array of random numbers rather easily. So now I'm going to generate the x coordinates by random dot uniform, right, from 0 to 1 and give me n of them. That's 1. Then I want to generate y, right? Again, same thing, uniform distribution from 0 to 1, n of it. Okay. Now I have all the coordinates. Now, of course, I can pair them because you see that if I take a peep at x, I don't want it to mess up the screen, so let me just show 5 numbers. All right, so I have 10,000 of these numbers streaming across, and the first number is to be paired with the first number of y, second number, right? So we can also try to stitch them together by zipping them and whatnot, but it's not necessary. It's not necessary. What we want to do is to decide the rim, the perimeter of each pair. Which part of the circle, that means there's a ring coming out, right? Which ring does it sit on? It can be any part of the ring, right? But what's the so-called squared radius does each pair give? And for that, we can call it z by squaring x and squaring y and adding them together. Okay, so now the length of z is the same as the length of x and the length of y, right? Because NumPy is able to do element y squaring and then summing, and because the lengths of x squared and y squared are the same, NumPy is able to just quickly produce the same sized vector containing the radius squared in some sense, right? So if whenever z is less than 1 according to our criteria here, yeah, whenever z is equal to x squared plus y squared, whenever z is less than 1, we would want to pick up the x and the y. Actually, y is not necessary because we're just trying to count how many darts are inside the unit circle. So we can say that give me those coordinates of x such that the z values, right, they are less than 1. Of course, you can try less than or equal to 1. Okay, so likewise, we can do y as well, but it's not really necessary because we just need to count the number of values in x2, right? So in x2, we can find the count, right? So the count of circle, let's say n circle, is the length of x2. And this will be the same as y2, so we don't have to really calculate. So it will be 7907. Okay, 7907. And based on our formula, right, the n circle divided by n is our bracket here. Yeah, because n circle is the count of number of darts inside the circle, and n is our total count, right? So this is our n. So n circle over n times 4 will be our approximation to pi. So let's try n circle 4 times n circle over n. Not bad, 3.1628. I already get 3.1, right? Not bad, not bad. It's just 10,000 calculations. How about larger n, right? So because of all the sequences we have done, I think it's repeatable. So instead of 10,000, let's try 1 million. 1 million n, right? And we're going to do x, then y, right? Then z. Calculate this and select our x2 for x whenever z is less than 1. And then we calculate our n circle like this. And then we calculate our final estimate, which is 3.14. The correct answer is 3.1415926. So 1415, we have 1408. That's for 1 million, right? So now that's 1 million. Let's try 100 million. Okay, I think it still works on my computer. That's 100 million. 100 million. So we're going to generate 100 million X. It's going to take, that's about 3 seconds. Then 100 million Y. And I don't want to look at the vector, right? It's really like, you just need to know the driver's seat, what you're doing. You don't want to know which spark plug is firing up, how much oil is being burned at that particular second. You don't want to think about all these details, right? So I don't want to look at the numbers. So long as there's no error, it means that we are doing the right thing. Of course, guided by our theory, our rules about the micro, right? So the components we know very well. This part involves a little bit of calculations, but using the GPU, it can be accelerated. Mine is not really doing that. Okay. So then now we do the extraction, the counting of number of dots that are inside the unit circle. And now we count how many of those, right? Not many. And then we use our formula to reintegrate back, right? Reintegrate back the counted numbers. Now it's 3.1415. Okay. Happy, but also not happy, right? Happy because the correct answer is, I think we have one. Yeah. So this is the correct pi, 3.1415926. Not bad, but not happy because we went from 1 million to 100 times more. 100 million, that's a lot, right? Only to get just one plus to maybe at the most 2 more decimal places. So we were good at about 1 to 2 decimal places. Now we get 4 decimal places. After 100 times more in our effort. All right, no doubt we don't spend a lot of effort, but 100 million is still 100 times more than 1 million. And the computation, even though very fast, is still 100 times more. And that sounds rather not very proportionate with our returns, which means this is not really a very efficient. It's effective because it does work. As we work harder and harder, as n increases, our accuracy increases. That means it is effective. We do get an approximation. And if we don't know anything about pi at all, now we get 3.1415. That can almost be useful for nearly everything that is practical. Okay, not enough for mathematics, but anything that's practical, 3.1415 is rather useful enough, right? But it is not efficient because when we increase our effort by 100 times more, it is we're throwing darts, right? And our net result, there's like the profit, the end result we are getting is not growing as fast, right? It's like growing by 2 more decimal places. Right? Some algorithms are able to, what we say, converge much more quickly, much more efficiently, right, than this very crude algorithm. But it works, right? That's what I want to show you. And imagine that we have no idea about pi, and all I need is just maybe even primary school concept of area and throwing darts and counting. And I can get this. See, the level of knowledge involved is not university level, right? It's not even high school level. It's just primary school level. And if we don't have computers, we don't have Python, we can do it manually, right? And we can do it. We don't need to understand complex mathematics like calculus, differentiation, Taylor series expansion to do all the much more efficient ways to find pi through approximations, right? Those are mathematical theoretic kind of approach. But simulation way, right? We certainly don't want to study pi using this method. But I'm trying to show you that the rules we know very clearly, right? The way to derive a governing set of rules, right? How to integrate it, integrate means assemble all the knowledge together to produce a simulation context or methodology that's appropriate to our goal, which is to find pi. It's also very clearly stated, right? We know very well how to decide if the dart is inside or outside. Very, very clear. Okay, maybe this part is not primary school. I don't know if your syllabus includes this. Okay, fine, right? But maybe earlier levels of high school. And if these days you can also search, how do I know whether a point xy is inside a circle or not? And you can readily get that from ChatGPT. Even though you don't understand why this is the case, but you will get this rule, right? So the rules are clear. Doesn't mean we know how to derive the rules. You can know this rule. You ask a mathematics professor, right? You get this without learning how you get this or why this is correct, right? So long as you get the rule described clearly, you can implement simulation. So that's great because many a times in business, in engineering, in challenges, in society, we do know the rules, but we just don't know maybe where are the loopholes, gaps, and all that. So what we do is we flood the rules, bombard the rules with a lot of entities. Can be humans, can be, if you're buying tickets, then you have 1 million people queuing up to buy tickets, right? You have no speed, maximum speed on the highways, but then you know that there's certain probability, certain distribution of people who will speed, right? And certain times of the day, the speeding cases will increase. The probability of a car speeding also depends on the time of day and so on. So you can describe those, right? And then have 100 million cars try to drive on that road, that simulated road, and see how many speeding cases you will find, right? And how many crashes, given probability of crash, and so on. So this simple example is to illustrate to you that very simple rules, and we don't even know why the rule is true. So long as you have the rule clearly delineates where the entity goes, where the dart here goes, inside or outside, right? And we have a distribution. For simplicity, I didn't gather data. I just used the existing standard uniform distribution from 0 to 1. But if I gather data, then it will be discrete table lookup. It will just be the same. I can generate InvCdf based on the discrete table lookup, right, to get a bunch of x and y. So once I get that, I can do counting. I can do empirical probability calculation. Empirical probability means count, right? The events happening divided by total count. So what is the probability that a dart falls inside the orange unit circle here? That's the empirical probability. So when we do simulation, we can then achieve this macro result. Where's the macro result? This ratio is actually the primary component of a macro result, right? This ratio is obtained from accumulating all the counts, right? Then divide it, massage it by 4 because of the governing rules. Then we get our final macro result, which is the estimation of pi itself. Right? So hopefully with this example, you can see both the simulation in action, right? Because of the simplicity of the goal and the components, and be inspired by the power of simulation methodologies because from personal teaching experience, this is truly right one such subject area where we learn new results that we didn't know before. Okay, other subjects like optimization, calculus, we can try to find the best in terms of optimization, right? Trying to find the best using calculus, trying to optimize certain functional results. And we can test whether that result is there or not. Because if it's not, then we will not be able to find any so-called best. For simulation, oftentimes we don't even know what to expect. We don't know at all sometimes, right? Whether the answer exists or not, whether the outcome that we are seeking exists on? Or to what degree does it exist? So we have no idea sometimes. In this example, we do know, of course, that pi will be will exist and will be that particular number on the screen. But in other cases, we don't even know the outcome. Then that's also when simulation, the return value is tremendous. Next is about the cost. Simulation is not cost free. There's no free lunch. It seems like, oh, you just let computer run and you get the result. You set n to be larger, go for your lunch. If you can, go for holidays for 10 days, then come back and your pi will be 10 decimal places accurate. There's no free lunch. In the sense that the time I spent here describing this to you will also be the time we spent, right? If I'm not presenting this as a tutorial or as a lesson to you guys, basically I will have to convince myself that what I'm doing in Python is correct, is guided by principle, correct? So I have to spend time to derive this. Now, at least this part can be understood, right? Can, at my level, at my primary school level, I can understand all these derivations, right? That I can understand the rules, that I can see whether all darts are accounted for, right? And I can assemble the result. Then governed by, or rather guided by these basic mathematical derivations, I then implement it in my so-called program. Now, of course, I didn't really write the program, but all my statements here can be, of course, codified and put as a program. And then this program will be implementing the simple rules 100 million times and then getting the systemic macro behavior of this, which is the ratio of darts inside the circle to the ratio of darts in the unit square itself. So hopefully then you can see the wider applications of simulation. With that, I thank you very much for your attention, and I'll see you in subsequent videos.